Chapter 1, Question 2 asks for the density of a 1 kilogram cylinder given the dimensions of diameter and height, which were 39 millimeters for both. I plugged in 39 to R and H to find the volume of the cylinder and inputted those to the density equation, which is mass over volume, to get a density of 2.15 times 10 to the negative fifth kilograms per millimeter cubed. For Chapter 2, Question 2 was asking for the time it takes for a nerve impulse to get from the toe to the brain. Approximately, the distance from the toe to the brain is 1.8 meters. The velocity given was 100 meters per second. So, assuming that velocity equals delta x over delta t, I did 100 meters per second equals 1.8 meters over delta t, and solved for delta t, getting 0.018 seconds. For Chapter 3, Question 2, it was asking for the value of y in the rectangular coordinate points and the value of r in the polar coordinate points. So using the equation x equals r cosine of theta and y equals r sine of theta was used to determine both. So using the known value of x, which is 2, and plugging that in to the equation that solves for x, we can determine r, since theta is also known, which is 30 degrees. R is equaling 2.31, and then using that r value, we are able to plug that into the equation that solves for y, using the same value for theta, which is 30 degrees, having a value of y equaling 1.16. For Chapter 4, Question 12, it is asking for the free fall acceleration on the planet that the astronaut is jumping on. So it is asking for variable letter G. In the problem, it gives us that the maximum range of distance that the astronaut is jumping is 15 meters, telling us that we should be using the range equation. So the range max equals the initial velocity squared over g, and given is the initial velocity, which is 3.00 meters per second, as well as the maximum range. So we're able to plug those into that equation to get a g value of 0.6 meters per second squared. Chapter 5, Question 2 is asking for the weight of a man on Jupiter given his weight on Earth. We also know that newtons are the type of unit to describe force, and force equals mass times acceleration, and in this case we are describing the free fall acceleration on these certain planets. Before calculating the amount of newtons the man weighs on Jupiter, we have to calculate the amount in kilograms that is equaling the amount of newtons that the man weighs on Earth. Doing that, we do 900 newtons equals x kilograms times 9.8 meters per second squared, because that models the force equals mass times acceleration equation. We use 9.8 meters per second squared specifically because that's the free falling acceleration that is present on Earth. After solving for the amount in kilograms that the man weighs, it is determined that he weighs 91.8 kilograms, and that value is going to be inputted into the same equation, force equals mass times acceleration, but in this case, acceleration is going to be 25.9 meters per second squared, because that is the free-falling acceleration found on Jupiter. Once we plug in 91.8 kilograms into the equation, we get that the force exerted on the man on Jupiter is 2.38 times 10 to the third power newtons. In Chapter 6, Question 2, it is asking us to determine the astronaut's orbital speed and the period of the orbit. We know that the astronaut orbiting around the moon is performing uniform circular motion. We also know that an object performing uniform circular motion's acceleration is equal to v squared over r. Given that we are provided acceleration, which is equaling 1.52 meters per second squared, as well as the radius, which is 1.70 times 10 to the 6th meters, we are able to calculate the velocity of the astronaut orbiting. However, the modification to the radius must be added because in the problem it explains that the orbit is circular and 100 kilometers above the surface of the moon. So we would have to add 100 kilometers to the already given radius of the moon. Once we have corrected for the modifications of the radius, we're able to plug that value into r and use 1.52 for acceleration and solve for velocity, which we get as 1.65 times 10 to the third meters per second, which is the speed of the orbital. Part B is asking for the period of orbit, and the period of orbit is defined as the amount of time it takes to orbit the moon once, which is the circumference of the moon, and circumference equals 2 pi r. We can plug in the modified radius that we have calculated before into r to determine the circumference of the moon. Since we now know the speed of the orbital, which is equaling 2 meters over seconds, and since we just calculated circumference in units of meters, we're able to plug both of those numbers in to calculate the amount of seconds it takes to orbit the circumference of the moon. Once we plug in all of those numbers, the amount of seconds it takes to orbit a period of the moon is 6.85 times 10 to the third seconds. For Chapter 7, question number 2, we are being asked for the work done on the raindrop by A, the gravitational force, and B, by the air resistance. First and foremost, we know that work is equal to force times delta R times cosine of theta, and force equals mass times gravity. So for part A, to determine the work done onto the raindrop by gravitational force, we are going to be plugging in 3.35 times 10 to the negative 5th kilograms because that is the mass of the raindrop falling. We're going to be using 9.8 meters per second squared as our gravitational force acting on the raindrop. We're going to be using 100 meters as our delta R value, and we're going to be using 0 degrees as our theta for cosine of theta. The reason why our theta value is 0 degrees is because the raindrop is falling vertically in the same direction that the force is being applied onto the raindrop, so the difference in angles is going to be 0, therefore cosine of 0 is 1. After multiplying all of those values together, the work done on the raindrop by the gravitational force is equal to 3.28 times 10 to the negative 2 joules. For part B, it is asking for us to calculate the work being done on the raindrop by the air resistance. Additionally, in the problem, it mentions that the raindrop is falling at a constant speed. Therefore, we can deduce that the sum of the forces acted upon the raindrop is going to equal 0. This means that the value of the resistive forces by the air is going to equal the same value that we calculated for part A. However, the sign is going to be negative rather than positive, which makes sense because in the diagram, the air resistance points upward in the negative direction, as we called gravitational force pointing downward in the positive direction. So when we plug all those numbers in with the modification for the resistive force, we get the work done on the raindrop by the air resistance equaling negative 3.28 times 10 to the negative 2nd joules.